So thank you very much for inviting me here. I'm really happy to be here for obvious reasons. I'm not at all clear why I'm here. This is without doubt one of the most challenging talks that I've been asked to give. It's just so much easier to go out there, put up your data and talk about it. Because it makes one sort of introspect a little bit and ask, what really have I done? And so I have given this talk an alternative title. It wasn't clear to me at the end of the day whether I was nowhere, somewhere, or everywhere. So I decided to leave it to you to decide. In having said that, I'm actually very grateful for Michael Arson's talk in the morning because I feel less embarrassed about the next slide, which is the disclaimer. I am not good at taking advice, and I'm not good at giving it either. So, but I can share with you how I got to do what I'm doing, and hope that it will, at the very least, entertain. I grew up always thinking about animals, ever since I can ever remember. I grew up always wanting to be in the outdoors. I was lucky enough to grow up in places where I could be out in the outdoors. And it was very clear to me that whatever I did in life had to involve real living animals around me. The night was the second fascination in my life. I've always loved the night and everything to do with it. Creatures of the night had a special fascination for me. And so I studied zoology for my undergrad and zoology for my master's, and I got out of all that without it killing my interest in animals, which, if you know how much of it is taught, is pretty amazing. But as luck would have it, when I came out of my master's and I really wanted to do wildlife ecology or animal behavior, in the late 70s, early 80s, there really wasn't a place in India where you could go out and do a PhD in something like this. There was the Bombay Natural History Society, and I tried hard to register with them, and they refused me. And then I had a major bout of hepatitis, which kept me down for several months. So at the end of the day, I ended up having to apply for PhD programs that were available. And I did that and hoped I wouldn't get in anywhere. And I got in everywhere. And that's how I ended up at the Tata Institute of Fundamental Research, which is where I did my PhD with Veronica Rodriguez, seen here actually many, many years later at the graduation of my own first student. And so I spent 5 to 6 years at the Tata Institute studying Drosophila genetics, genetics of the chemosensory system. I was Veronica's first student. We were both young and enthusiastic in very different ways. She was a young PI and out there to get stuff done. And I was a completely rebellious student. But I think at the end of that, we became really, really good friends. And she and Ubaid were my mentors through 5 wonderful years at TIFR, where I learned a lot of things. But at the end of 5 years, I realized that genetics was not what I wanted to do. And I needed to get out and get back into animal behavior and ecology. And I had to make that switch, and I had to make it at that point. And I didn't know how to do this. I wanted to work with animal navigation or animal communication, that much I knew. I had read up so much about it and about various groups working in Europe and the US. And I did the usual things, wrote to people, contacted them, visited labs, wrote up proposals, did the whole thing, and 1.5 years down the line was zilch. And so at that point, you start to sort of lower your, you become less fussy, and you will ask, okay, is there anything else related that I can do? So I actually started looking at ads. And there came out an ad in Nature from Jerry Pollack at McGill University for a postdoctoral fellow to do intracellular neurophysiology of the auditory system. Well, I was familiar with Jerry's work. I knew he did a lot of interesting work on cricket acoustic communication. I wasn't a good physiologist. I had no real interest in doing so. I wrote the application anyway and thought it would end up where it should end up, in the waste paper basket. I got an offer for the postdoc. Many years later, I picked up the courage to ask Jerry, how many people applied for that position? He said, oh, 70. I said, huh? From where? United States and Canada. I said, what? You picked me? I said, why? He said, your letter. And I said, what about me? He said, your letter stood out. Because I had said, I trained in genetics, I want to do animal behavior, I'm not interested in physiology. Here's what I want to do. And he said, anyone who could be so brutally honest in a job application was someone I wanted in my lab. So this is just to tell you that it takes all types to make a word. So it was at McGill that I got into doing acoustic communication. And while I was there, I read a lot of the literature, and as I did that, I kept coming across the papers of Dartmouth and Helverson on pattern recognition in grasshoppers, and I could tell that they were just a class apart. Right? These were incredible experiments, incredible behavioral experiments. They were hard to understand, and when you finally understood them, it was always, wow, how could anyone be so clever? Okay. They were really clever, really elegant experiments. They inspired me just to read them. So I went to Jerry and I said, who is she? And how can I meet her? And he said, well, she's one of the best people around, but you know, she doesn't really have a job. She gave up a job long ago, although she's an active scientist. You won't see her at any conferences. And then he said, hey, why don't we invite her for a month? And that's what we did, and that's how I met Dartmouth and Helverson. And she was everything that I had ever imagined she would be and more. An absolutely wonderful person. And so then she said, you know, when you finish up at McGill, you should come to Germany so we do some work together. And then we started the same cycle of looking for money and writing proposals and stuff. And again, nothing worked. So I had 1 week left to leave Canada, no postdoc positions lined up. Everything came out negative. All proposals said, forget it. So I was depressed, and I wrote, well, what do you do when that happens? You go home, because at least the dollars you have can go longer in India. And I wrote her an email saying, well, that was a good thing, we tried, too bad, I'm going home. So I got an answer, a reply the next day. And that reply literally changed my life. So that's why I call it turning point, right? It's not a reply you expect to get. Okay? So she said, yeah, too bad. Yeah. Why should we let money get in the way of doing things we like to in life? Yeah. You know, Germany is on the way home. If you get off at Frankfurt, I promise you, you will not starve. So I looked at that and I said, huh? What a great idea. So I went and got a tourist visa, and I got off the plane at Frankfurt. That's how I got into my second postdoc. I ended up there and I said, here I am. Okay? And that's how we started out working with pattern recognition in grasshoppers. And it was fantastic because, just think about it, I had no formal position really, and neither had she. Okay? And the whole lab just kept me going. I have no idea how, but some pieces of money, and kept me going for a very long time, for 2 years. The other person who was my godfather really was Norbert Elsner at Göttingen, who also used to come and give me little cash presents. They would say, no, but I don't even work for you. And he would say, never ask somebody who's giving you cash why they're giving it to you. Okay. So that's how I worked for 2 years in Germany, 2 of the most fantastic years of my life, where I learned much from Otto and Dagmar. Unfortunately, all three passed away. And then I was applying for my money for a proper postdoc fellowship in Germany, and I was applying for jobs back in India. And believe it or not, on the very same day, I got 2 letters. I got one from Germany, where I got a good postdoctoral fellowship with lots of money, and I got the offer from the Indian Institute of Science in Bangalore at the Center for Ecological Sciences for an assistant professor position for a very small amount of money. But in those days, your position was a permanent position. And so, well, it's home, it's where I like to be, it's in a department I would like to be in, and that's how I came back. And the letter said, come back, come back, come back quickly, 3 months. We won't give you more than 3 months. Why not? Come back. And so you come back, and the Institute of Science, I have a very deep affection for it. But the Institute of Science is this enormous 100-year-old institution with a 100-year-old bureaucracy. And then you come back and you realize really that nobody even seems to have figured out that you've come in and joined, except the person who takes your fingerprint when you get in, including in your department. And so you don't really have space, you don't have equipment, you don't have money, you don't have anyone to tell you how to get in with it. And so you get irritated, and you keep trying to fight and do this, and you can keep on cribbing. It took me 2 years to get a room. It took me 3 years to get me money. It took me longer than that to get my first student. So what do you do in this time? What did I do? Right? Well, there was teaching, and I set up a new course, and it was great because I had an entire year to spend on really making this course shipshape. And then I spent my time fighting. I fought everyone from top to bottom. Yeah. And what do you do when you've got such a large body of bureaucracy which doesn't really budge? You find it's more to get it out of your system. So what do? You take a walk, and if you happen to live on as wonderful a campus as I do, you see a lot of interesting things. So I would spend my evenings tracking crickets, listening to them. And I had my own little recorder. I would make recordings. And I would collect crickets, crickets and recordings. And then I needed to look at them. I had no way to, because actually I didn't even have a computer. So I went and bought components in the market. My uncle had an old computer that he opened up, and he and I assembled my first computer. And that's how I managed to start looking at my signals. And to look at my animals, I would go to the GKVK campus, to the entomology department, to the lab of Professor Balakrishnan, who welcomed me in there and actually taught me how to identify these animals. And I would sit there and try and figure out what these animals were. And of course I had their recordings, and that's how I ended up spending the first couple of years actually trying to get into systematics. I had all these animals, I couldn't identify them, wanted to figure out what they were doing, and I started reading. It became increasingly clear that systematics is a really sort of underrated field. It's an enormously difficult field. It's really hard to make a species identification. And with crickets, of course, we have the additional character of song together with morphology. And I thought, wouldn't it be to see how good song alone is, or combinations of song and morphological characters are in actually delineating species. And I used an approach that was already old at the time it started, 20 years outdated. It was numerical taxonomy. And I thought it was such a fresh idea. Smeeth and Sokal advocated, instead of just using diagnostic characters under the microscope, you measure a whole lot of things about animals, you put it through multivariate analysis, and you see with what accuracy things get picked up. So hey, I had crickets, I had songs, so let's try this. And I'm really thrilled because I got over 95% correct identification, using this approach. And very few people had actually taken it through the whole process rigorously. So I said, this should be publishable work. The reason I put these two up is because I just want to highlight the early days. And so I had this piece of work that I actually managed to do, and I thought was pretty good. And of course, no one wanted it, right? It was outdated. And systematics had moved into cladistics. Okay? And nobody wanted, no systematics journal wanted it. I finally got it into review, and then of course didn't want it either. The problem was the fad. Systematics had moved into cladistics. I said, why are you doing this stuff? But actually, cladistics wasn't, and really I would say isn't, solving the problem of species identification. What we need in the tropics, where we have large numbers of species and large numbers of unidentified species, are quick ways to do this. Quick, reliable ways to do this. And nothing that was happening in the cladistics business was going to add to this. And the disconnect between theory of species boundaries and phylogenetics and what we need in the tropics became very obvious to me. So I decided to write an article about it. And this article, weirdly enough, just breezed through in systematic biology. I realized today that this actually is the only article of mine that has made any kind of real impact, if you like. The number of people who actually read it, the number of people who wrote back to me. And the best for me was, within that year, when a package arrived in the mail, a huge package, and I wondered what it was, from someone I didn't know. Turned out to be someone from UCLA, someone doing environmental law, who actually used this to argue a court case and won a conservation battle for a piece of land. And I felt vindicated having actually done this at that point. Students, getting students was hard at the point, and I had to battle to change the entire exam system for 4 to 5 years before we could get in the kinds of students that we actually did. But I also had a lot of fun walking the parks, footloose and fancy-free. And I walked up and down simply looking and listening, and when I reached Kudremukh, I knew I had come home. Why? Just walking there and listening, the tremendous acoustic diversity and the cacophony told me that this was a place where there was exciting stuff to be done with insect acoustics. And the question I tried to tackle was communication in this cacophony. How does each species manage to communicate its message across to, if you like, the intended receiver? In crickets, it's male crickets calling out to females, when everybody is calling out altogether. Is this a good research question? I went back and read up and found that there had been very little done, and certainly not on the ambitious scale of an entire rainforest. So one of my first PhD students was very enthusiastic, and she and I went in and said, hey, let's start tracking the signalers. And because we didn't really have any mentors or peers to tell us that this is an impossible job, we actually managed within 3 years to identify most of these animals. And the question that we tried to answer there was whether there are strategies that senders and receivers use to combat acoustic interference. And the sender strategies, which is what we started with, the hypothesis would be that the core structures and spatial-temporal signaling patterns of species in acoustic communities may result from the need to minimize acoustic interference. I'll cut a long story short and just give you the answer. Some years down the line, what we find is that if there are strategies, it's in the core structures themselves rather than the spatio-temporal signaling patterns of species in these communities that may have been driven from the need to minimize masking interference. But how do you test a hypothesis like this? We needed a way to actually measure or to estimate masking interference. And currently, there wasn't a way really to do this, because in order to do this, you need to know a lot of things. You need to take into account a lot of factors. You need to know where senders are in relation to each other and in relation to receivers, how loudly they call, what happens to the kinds of sounds they produce as they are put out in the forest, in the environment. And then there's the temporal angle that also has to be integrated into this. And it became increasingly clear to me that the way in which people were actually examining masking interference by simply looking at signal structure was totally inadequate. And that's when we decided to try and come up with a 3D simulation model that would try and integrate all of these factors. And my student Manjari Jain was the one who actually did this. Well, we had a problem, and this kept us busy for more than 2 years, which was that it became very difficult for us when we had natural courses in which we were trying to model these acoustic broadcast spheres. And what you really need to know is what one animal sitting over here experiences of interference from all of its neighbors, not from one or two of them. And this turned out to be a somewhat formidable problem beyond my mathematical and computational abilities and Manjari's. And one day, a young man walked into my lab. He was a computer engineer. He had seen our work on the web, found it interesting. He was just taking up a job with, I think at the time it was Yahoo. And I told him about this, and he said, let me give it a go. And within 3 weeks, working in his spare time, he actually managed to solve this so that we now have a nice 3D simulation model. We also spent a lot of time, at least for all of the species in the understory, actually getting all of these data. So we actually had most of these numbers, and we could plug them into the model. And what we found when we did this is that when you take all the axes of separation into account, that is time, space, intensity, frequency, even if animals were to pay no attention to each other, the median masking probabilities that we saw were close to zero for natural courses. Basically, it meant it's a pretty quiet place. Okay, just to finish the science part of it, it seems to be, at least all of our estimates tell us, that there doesn't seem to be that much masking interference. But that probably, does that mean that we're looking at the solution to the problem? In other words, is this particular set of signals an optimal solution to minimize acoustic interference? We haven't got the answer yet, but we have a nice simulation model. And I hope that we'll be able, it's really a lot of number crunching from now on. The hard part is over. And I hope that we'll be able to actually answer this question of whether natural acoustic communities that we see are actually optimal, if you think of it in terms of the communication network. something we hope to do in the future. Now I'll take a little aside to tell you a little story about the publication of this paper, because it was heart-wrenching. This was only 2 years ago. So we did all of this work and we were really, really pleased with ourselves. And we really thought we'd done something important in the little pond of a field called transcript theories. And it was when we started to publish it that we realized that we were the only ones in the world who thought so. I think this has to be my record, my paper of record rejects. I think I had 9 rejects without review from just about any kind of journal I could think of. But when acoustics journals begin to reject it, saying they don't think it's worth anything, and then you've got 9 rejects, it makes you wonder, and it shakes you up a bit. And I'd spent 10 years on this. And I said, well, could I have been so wrong? And this is a very frightening thought. Could I have been so wrong? And for a while, I did believe it. And I just put the paper aside. And then I said, hey, let me think of it the other way. Let me think of it that I'm writing everyone else's. And let me try and find somebody who might read this and actually understand what I'm trying to do. So then I researched editors. I researched journal editors. And when I hit John Endler, I knew I'd found the right person, because for those of you who don't know, John Endler's done a lot of work on the interface of acoustics, ecology, and evolution. And the end result was that the paper moves through and it went to evolutionary ecology. I'll just spend 2 minutes telling you a little bit about some of the more recent stuff. Well, we spent a lot of time here, and then we wanted to begin to look at receivers, and this is where I needed help. Looking at receivers meant looking at ears, looking at mechanics, looking at eardrums, looking at physiology. I'm not really well trained to do that. And so I collaborated with Daniel Robert at the University of Bristol, who's an expert at biomechanics. And we started looking at the ears of these animals. We started looking at the tuning of these ears. I'm not going to go into the data. But the interesting thing that I wanted to highlight, is that the ear of the species that I put up here acts as a low-pass filter, which basically means it lets low frequencies pass and cuts off high frequencies. If you look at a range of insect ears, what you begin to see is that there are all kinds of filters. There are low-pass filters, there are band-pass filters, there are all-pass filters. And my former student, Natasha Matre, who did a lot of these, also recently found active tuning. So basically, all of these weird ear structures that we see in these wonderful crickets are actually different from each other. They're all different kinds of filters. I think it's just enormously interesting stuff for people interested in looking at how such tiny mechanical filters are made. Similarly, there's a diversity of resonators that might work quite differently from each other. And we started looking at some of these. We looked at tree crickets who actually change their frequency with temperature. I'm running out of time, so I'm not going to go through this science. And one of the problems that I've been very puzzled about is that there are 2 major clades of crickets. There are the true crickets and there are the bush crickets and the clay crickets. The true crickets, they're evolutionarily similarly of the same age. The true crickets have, over so many millions of years, been very conservative and they sing only between 3 and 9 kilohertz, whereas the katydids seem to be able to roam anywhere in the acoustic spectrum from the point of view of sound production. And I wondered what this phylogenetic constraint could be, and I hypothesized that it might lie in the mechanics, which is why I set up a collaboration. The Center for Nanoscience and Engineering came up at IISc very recently, and luckily for me, Rudy Pratap, who heads it, was extremely excited by this problem. And I've called this the strength of a promise because it really started when I gave a behavioral ecology talk in the mechanical engineering department. And he looked at it and he said, these are incredible creatures, we should understand how they make these. And I will make you a loudspeaker that is as small as a cricket and will emit sounds exactly like one. I didn't take him very seriously, but he put a PhD student on it. I think a few months down the line we're going to have it. The last thing I'd like to talk about, so we looked at this communication network. We also looked at it in terms of signal evolution and tried to examine some of the drivers of signal evolution. We spent 10 years examining habitat acoustics and mosquito control. We began to look at phylogenetic constraints, but the big driver is predation. This is what we started looking at a few years ago. Since bats are major predators, started looking at these and really got some surprising results. Well, the textbooks say it's the males that are calling, bats will open on the males and take them. We found exactly the opposite. Males call, females don't call. But it's the females who are getting eaten in large numbers. We don't understand this, but we're sure that this is true. We don't understand whether it's specific to the paleotropics, specific to our system. Well, it's simply that males are loud, conspicuous, attract attention to themselves. Females are unseen, unheard, lurking in the undergrowth. They don't get any attention. And maybe that's why most attention has been on the male end. So I hope I've convinced you that local biodiversity is really a treasure house for biologists, engineers, yes, and physicists. And I think there's tremendous opportunity for young biologists in India if they get off the beaten track. Because our biodiversity is so incredible that it will ensure that you find something new and exciting. You can find new systems that could either challenge or validate so-called model systems. Or new discoveries. And new discoveries always fuel new hypotheses or challenge old ones. The problem, of course, for young investigators to get off the beaten track, I think we've discussed this a lot in our discussions, are the old investigators. So I'll put some food for thought up there. I see science as it's being done today. The paradigm in which it's being done is that of professional competitive sport, and in particular, the racetrack. And I really question whether that's the best paradigm in which to do any evaluations. Especially when we live in a country of such high biodiversity, to me it seems strange to keep talented young people on a racetrack when the most exciting discoveries are off the beaten track. I believe we need to make use of this one enormous advantage one has of living and working in India, which is our tremendous biodiversity. And I do hope that the system will adapt to allow this. I believe it should, I believe it can. And I'd like to see the day when, rather than us saying, is it possible to really do good science in India, we should really be saying, I do good, novel, exciting, and interesting science because I live and work in India. As I can say today, with immense pride, because of wonderfully motivated, talented students, postdocs, and assistants, wonderfully generous collaborators and colleagues, especially at the Indian Institute of Science, and really in spite of all the kinds of obstacles and delays that are very peculiar to the Indian system, but hey, we're Indians, we know how to navigate global.